It is a really useful tool that we have to be able to draw the valence electrons that a atom has. Now, drawing something like this that I showed you on the previous page can get very tedious. And these inside electrons actually don't tell us much. What we really care about are these outside electrons, the ones that are able to come in contact with other atoms. So in order to summarize the electrons around an atom, we have something called the Lewis dot structure. And the Lewis dot structure is really, really simple. So let's say I have the element carbon. And I want to draw a Lewis dot structure. So I'm going to use dots to represent electrons, and I figure out how many valence electrons carbon has. So carbon's right here, and it's in the 1, 2, 3, 4th tall column on the periodic table, so it has 4 valence electrons. So I'm going to put 1, 2, 3, 4 valence electrons around carbon. I'm done. That is it. That's all I have to do for a valence structure, or Lewis dot structure. Notice how I put 1 electron on each side of that carbon. And this is to follow Hund's rule, where I put 1 electron as far apart as I can from each other in the same energy level before I pair them. So if I look at a bigger atom, let's say sulfur, sulfur is in the 1, 2, 3, 4, 5, 6th tall column, so that means it has 6 valence electrons. I'm going to put 1, 2, 3, 4, 5, 6 electrons. Notice how I didn't pair them until I put 1 electron on each side. One more I'll do is, let's say I do xenon. I need to know its Lewis structure. Well, it's in the last column. It means it has a complete octet. And we'll look. And it has 8 valence electrons. And that is a complete valence shell. Remember, there is an exception. Helium has a complete shell, but it only has 2 valence electrons on it. Just never forget that that actually happens. So we can have 8 electrons to complete our valence shell. Now, what if I have an ion? So let's take, for example, calcium. Calcium has 2 valence electrons, but it wants to have, or it would be more stable if it had a complete octet. It has 2 options that can occur. It can gain 6 more electrons to give it 8, just like xenon, or it could lose all of its electrons, 2 electrons, which would be more favorable to occur. Well, losing 2 electrons would require less energy, so in order to gain a complete octet, calcium would lose both electrons, giving it a positive 2 charge. And note that when I have a charge on my atom, it ends up in brackets with the charge on the outside. If I had, let's say, nitrogen, nitrogen has 5 valence electrons. Now it can either gain 3 electrons or lose 5. Gaining 3 is easier than losing 5. So I would get nitrogen with now 8 valence electrons, and I'm going to draw the ones that were added in a different color. So I started with the 5, and I add 6, 7, 8, and because I added 3 electrons, it now has a negative 3 charge. So an atom is either going to lose electrons or gain electrons to be stable. So it'll either end up like calcium that has no valence electrons. It's lost its outer shell, so now the inner shell becomes valence and has a complete octet. Or it can gain electrons to get that complete octet becoming negative. Now, because we know that all the elements in the same group, the same column on the periodic table, have the same number of valence electrons, we can actually predict the charges as ions for any element in the tall columns, the tall groups on the periodic table. And feel free to write these on your own periodic table. So these are the charges that these elements get when they are in the ionic form, when they are most stable, when they have a complete octet. So the elements in the first column here, they all have one valent electron. Now they could gain 7 electrons or they could lose 1 electron. Well, it takes less energy just to lose 1 electron, so if you lose an electron, you get a positive 1 charge. In the second column, they all have 2 valent electrons, so they could gain 6 or they could lose 2 electrons. They tend to lose 2, so these all get a plus 2 charge. Now the ones in the middle, just like how we didn't know what the number of valent electrons were, we don't know the charges they're going to get. These are known as the transition metals. They can actually get several different charges as ions, so we're not going to worry about them quite yet. In the third column, we have 3 valent electrons. It's easier to lose 3 electrons than gain 5, so all of these elements will have a plus 3 charge when they are ions. In the next column, these have 4 valence electrons, so they could gain 4 or they could lose 4, and it's just as likely for them to do either, so these will have a plus or minus 4 charge. So they could gain 4 or lose 4 electrons. In the next column, these all have 5 valence electrons. Is it easier to lose 5 electrons or gain 3? Well, they're going to gain 3, so they will get a negative 3 charge. The next column, these all have 6 valence electrons, so they're likely to gain 2 electrons to have a complete octet, so these will have a negative 2 charge. And in this column here, the halogens, these have 7 valent electrons. They're likely to gain 1, so these will have a negative 1 charge. And lastly, we have the noble gases. Well, they already have 8 valent electrons, so these are all actually not likely to become atoms, and these always get a 0 charge. It is very rare to see a noble gas with a charge.